There's a silent, persistent question that echoes through the vast, cold reaches of the cosmos, a question that has haunted philosophers and scientists alike for millennia. How did we get here? How did times anything get here? We live in an epoch of astonishing discovery, where the universe, once a distant, enigmatic tapestry, is now beginning to reveal its intricate weave, thread by magnificent thread, and sometimes one of those threads pulls at an entire segment of our understanding, forcing us to re-examine not just the thread itself, but the loom upon which it was spun. For centuries, our view of the universe was limited to what our naked eyes could perceive, and later, what rudimentary telescopes could magnify. We charted the heavens, identified familiar constellations, and marveled at the Milky Way, a faint, ethereal band of light stretching across the night sky. With time, our instruments grew more sophisticated, and our understanding expanded. Galileo turned his telescope skyward, revealing moons orbiting Jupiter and the true nature of our sun-centered system. Herschel meticulously mapped the stars, suggesting our galaxy was a vast, disc-shaped entity. And in the early 20th century, Edwin Hubble's groundbreaking observations confirmed the existence of galaxies beyond our own, transforming our universe from a single island of stars into an archipelago of billions. He also noticed that these galaxies were rushing away from us, their light stretched into longer, redder wavelengths, a phenomenon we now call redshift. This was the first empirical hint that the universe itself was expanding, a revelation that would eventually lead to the Big Bang theory. The Big Bang isn't an explosion in space, but rather an expansion of time-space, an event that marked the beginning of time and the emergence of all matter and energy. Our current cosmological model, refined over decades, paints a picture of a universe that began incredibly hot and dense, then cooled and expanded. In its infancy, it was a chaotic soup of fundamental particles. As it cooled, these particles coalesced into atoms, primarily hydrogen and helium. Over hundreds of millions of years, gravity began to pull these diffuse clouds of gas together, forming the first stars, and eventually, the first galaxies. These early galaxies, we believed, were smaller, more irregular, and still very much in their formative stages, gradually evolving into the majestic spirals and massive ellipticals we observe today. It was a slow, deliberate process, guided by the fundamental forces of nature, taking billions of years to sculpt the grand structures we now inhabit. And then, the James Webb Space Telescope came along. Its golden mirrors, designed to capture the faint infrared glow from the most distant corners of the cosmos, peered back in time with unprecedented clarity. It has begun to reveal secrets that challenge our carefully constructed timelines, pushing the boundaries of our knowledge and sometimes our credulity. Recently, the JWST made an observation that sent a ripple of excitement and consternation through the astronomical community. Two intrepid Indian astronomers, sifting through the treasure trove of JWST data, discovered something truly astonishing: a galaxy they've named Alaknanda. Now, Alaknanda itself isn't just another distant galaxy. It's a fully formed, grand designed spiral galaxy. And here's the kicker. It exists at a staggering cosmic distance, so far away that the light we are seeing from it began its journey when the universe was only 1.5 billion years old. Let that sink in for a moment. Our own Milky Way, a classic grand design spiral, is estimated to be around 10 billion years old. Its spiral arms, its central bulge, its organized structure are all products of billions of years of gravitational dance, of star formation, of mergers, and the subtle, persistent shaping force of density waves. We've always understood that it takes an immense amount of time for a galaxy to mature into such an elegant form. Yet Alaknanda, observed when the universe was but a cosmic toddler, presents itself as a fully fledged, grown-up spiral. This discovery, quite frankly, is a profound challenge to our existing models of galactic evolution. It's like finding a fully developed human adult living just a few years after the first single-celled organisms appeared on Earth. It fundamentally changes our timeline for cosmic maturation. We're not talking about some amorphous blob of stars, mind you. Alaknanda possesses the distinct hallmarks of a grand design spiral. Two prominent spiral arms coiling elegantly around a bright, rounded central bulge. It spans a diameter of roughly 30,000 light-years, a considerable size for any galaxy, let alone one from the universe's early epochs. And it's not just sitting there idly. Alaknanda is a stellar nursery on steroids. It's furiously producing new stars at a rate equivalent to 60 solar masses per year. That's 60 new suns forming every single year. This rate is 20 times higher than our Milky Way's current star formation rate. What's even more remarkable is that approximately half of Alaknonda's stars have formed within a mere 200 million years. In cosmic terms, 200 million years is a blink of an eye. This implies an incredibly rapid, almost violent, burst of star formation early in its history, leading to a quick assembly of its magnificent structure. How did the James Webb Space Telescope manage to glimpse such an ancient, distant wonder? It employed a celestial cheat code. Gravitational lensing, JWST, was pointed towards a massive galaxy cluster known as Abell 2744, or Pandora's cluster. This cluster, itself billions of light-years away, acts as a cosmic magnifying glass. Its immense gravitational field warps the fabric of spacetime around it, bending and amplifying the light from objects far, far behind it. Alaknanda, located billions of light-years beyond Pandora's cluster, had its faint signal magnified and stretched, allowing JWST to resolve its detailed structure. The telescope's incredible sensitivity, combined with the use of 21 different filters to capture light across a wide spectrum, allowed astronomers to reconstruct this detailed portrait of a nascent, yet remarkably mature galaxy. This isn't just an isolated anomaly. The implication is that if we found one such galaxy, there must be many more. The early universe, far from being a tranquil era of slow and steady galactic growth, appears to have been a surprisingly dynamic and efficient constructor of complex systems. The question now becomes, how? We have a few compelling hypotheses. One possibility is that Alaknanda grew rapidly by continually accreting streams of cold gas. This steady influx of fresh material could have fueled an accelerated process of star formation and, crucially, allowed density waves to propagate and sculpt the galaxy's distinctive spiral arms much faster than our current models predict. Density waves are crucial to spiral structure. They aren't physical waves of stars moving through the galaxy. Rather, they are areas where gas and dust accumulate, becoming denser, which then triggers star formation. These waves move through the stellar disk, continually refreshing the spiral patterns. For this to happen so early, the conditions in the primordial universe must have been incredibly conducive to such rapid accretion and organization. Another intriguing possibility, perhaps even more dramatic, involves galactic collisions. The early universe was a much smaller, denser place, with galaxies forming in closer proximity to each other. It's plausible that Alaknanda wasn't formed in serene isolation, but was instead the product of a furious merger event between two or more smaller galaxies. Such a collision could have rapidly funneled vast quantities of gas to the center, triggering an intense burst of star formation, and perhaps, through gravitational interactions, sculpted the two prominent spiral arms we observe. Galactic mergers are known to be powerful drivers of evolution, and in the early, crowded universe, they might have been more common and more impactful than we previously imagined. Now, before anyone jumps to conclusions about the Big Bang being broken or cosmology being a farce, let me be clear. This discovery does not undermine the Big Bang theory. The Big Bang describes the origin and overall expansion of the universe. What Alaknanda challenges are specific aspects of extragalactic astrophysics, the study of how galaxies themselves form and evolve within that expanding universe. It forces us to refine our understanding of galactic formation timescales and the precise mechanisms by which large, organized structures emerge from the primordial soup. It's a testament to the scientific method. When observations contradict predictions, we don't discard the whole edifice. We adjust our models, we ask new questions, and we deepen our understanding. The next step, as always, is more observation. With one Alaknanda identified, astronomers are already re-examining other distant galaxies in the JWST data, searching for more of these early bloomers. Future observations will aim to build a statistical sample, allowing us to determine just how common these grand design spirals were in the early universe. Furthermore, telescopes like ALMA, the Atacama Large Millimeter/Submillimeter Array, will be turned towards Alaknanda. ALMA, which observes in radio wavelengths, can detect the chemical composition of gas and dust within the galaxy, providing crucial clues about the conditions of its formation and the types of stars that were born within it. By studying these elements, we can piece together a more comprehensive story of how Alaknanda defied our expectations and grew into such a magnificent structure so rapidly. This is the very essence of scientific exploration, a continuous journey of discovery, where each answer often leads to a dozen new questions. Alaknanda reminds us that the universe is far more complex, and perhaps more efficient, than we had ever dared to imagine. It urges us to remain humble, to challenge our assumptions, and to always look deeper into the cosmic abyss, for that is where the most profound truths often reside. That's it for today. If you enjoyed this deep dive, hit that subscribe button. Stay curious, and keep your eyes on the skies. I'll see you in the next one.